Okay, welcome back. This is the second part of the proof of the three-dimensional result of Richard Hamilton. We've just shown in the last lecture that non-negative Ricci curvature is preserved and that uniform positive Ricci curvature is also preserved. Now we have to prove the actual pinching estimate. To do that, it turns out we have to somehow break the scaling invariance, as you know, the pinching estimate. And the proof is quite brutal. We just look at the pinching estimate we want and compute the evolution equation of the quotient. Okay, so theorem Hamilton 82. If the Ricci curvature on a compact three-manifold satisfies G bigger than epsilon r times Gij, then there exists a delta greater than 0 depending only on this epsilon and the constant C0, which just depends on the initial metric, such that the traceless part of the Ricci tensor is bounded by r to the 2 minus delta. And this is, of course, since the Y tensor is not there in 3 dimensions, this is exactly the pinching condition that we had in our general theorem. So as a corollary, it follows that the Huisken, if Ricci of G0 is greater than 0 on M3, G0, then the solution of the normalized Ricci flow ddt Gij equals minus 2 Rij plus 2/3 little r Gij, where r was the average of the scalar curvature, converges smoothly, actually exponentially fast, as we proved, to a spherical space form. In particular, then any three-manifold that admits a metric of positive Ricci curvature must be diffeomorphic to a spherical space form, and the spherical space forms in 3 dimensions are known. They are known in any dimension actually. It's diffeomorphic to either S3 to RP3, which is just S3 divided by the antipodal map, or to one of the length spaces LPQ, which is S3 divided by a discrete group of isometries acting freely on S3, and in this case, of course, it's exactly known what these groups are. They are the rotations that you get in R2 cross R2 along the circles in the two factors of R4, restricted to the 3-sphere. So it's completely known what these spaces are, and that was the famous theorem of Hamilton in 1982. Okay, so we have to prove this estimate, and we simply take the quotient of the left-hand side with the right-hand side and show that we can, depending on epsilon, choose the delta so small that this quotient of Ricci 0 squared and r to the 2 minus delta is bounded by its initial data. And then the C0 is just the initial constant such that this is true. It will remain smooth, it will remain true with a fixed epsilon only depending on the epsilon which comes from the uniformly positive Ricci curvature. Okay, proof. From ddt Rij equals Laplacian of Rij minus Qij, which we had, and Qij was this thing with 6 times square of Ricci and so on. We can compute that ddt of Ricci squared is equal to the Laplacian of Ricci squared minus, we had this evolution equation before, minus the gradient of Ricci squared, but now it's important what are the actual terms on the right hand side. Remember, we were using something like that in the proof of the gradient estimate. And then we just knew on the right hand side there's some terms that had the right structure, but now we need to know exactly what it is. And what it turns out, if you do the little computation, you get minus 8 times the trace of Ricci cubed, and then you get minus 2 times the trace cubed, and then you get the other algebraic term that remains, namely the scalar curvature times the Ricci curvature squared. So you have sort of the sum of the principal curvatures cubed. Here you have the sum times the sum of the squares, and here you have the sum of the cubes. And this is a polynomial of 3rd order. And on the other hand, you have we have that ddt of r is equal to Laplacian of r plus 2 times Ricci squared. Okay? So now, then for any not any, we know what we want. We want gamma equals 2 to the minus delta, you can do the following computation for any gamma, but the gamma I have in mind is of course 2 to the minus delta. We compute what is ddt of Ricci squared divided by r to the 2 minus delta. And what you end up with is, let me see, did I say this right? No, you have to take the trace free part here, actually, right, which is ddt of Ricci squared minus 1/3 r squared divided by r to the 2 minus delta. Okay. Now, if the this is of course the same as ddt of Ricci squared divided by r to the gamma minus 1/3 ddt of r to the delta. Okay. So, and this is easy to compute. The crucial thing is to compute this. Now, ddt of Ricci squared divided by r to the gamma is equal to, now put this in, you get 1 on r to the gamma times Laplacian of Ricci squared minus 2 gradient Ricci squared plus minus 8 trace of Ricci cubed minus 2r cubed plus 10 r Ricci squared. And then you get from the denominator minus gamma Ricci squared divided by r to the gamma plus 1 times Laplacian of r plus 2 times Ricci squared. And now it becomes, we want this into a nice form. And it's going to be a tedious computation, but routine. You have to collect the absolute terms, which is easy. You combine just these terms with this 2 Ricci squared term on the one hand. And on the other hand, you'd have to think of these terms with the derivatives. And you want to end up with the Laplacian of the same quantity. So the idea is not to try to keep transforming, but compute the Laplacian of this quantity, and then some of these terms will pop up, and you collect the difference, and this gives the computation. Maybe I can see this form. So also you compute that the Laplacian of Ricci squared on r to the gamma is equal to, well, you get 1 on r, you get gradient I of, and then you get 1 on r to the gamma times gradient I of Ricci squared minus Ricci squared divided by r to the gamma plus 1 times gradient IR. And when you keep computing, you get the term that you were looking for, Laplace Ricci squared squared divided by r to the gamma, which is this term. And then you get the cross term coming from here minus gamma, and because you get another one from here, we can write minus 2 gamma divided by r to the gamma plus 1 times gradient I r gradient I Ricci squared. And then from here, one of them we already had, where the derivative was going on the top. The other one is Ricci squared divided by r to the gamma times Laplace r, which is the other term we wanted from here. And here I obviously forgot a gamma, right? And so we have the gamma that we need from here, okay? And then it remains to differentiate this one. So we get plus gamma times gamma plus 1 divided by r to the gamma plus 2 times gradient r times Ricci squared times gradient of r squared. Okay? And now you collect terms. And the point is that you get something on which you can just use the scalar maximum principle. The scalar maximum principle. Nothing else. So then you get, and you also have to compute the evolution equation of r to the gamma. But then you get, by collecting terms, and using for f equals Ricci squared Ricci squared over r to the gamma, that gradient I, you need this equation again. You need that this is 1 on r to the gamma gradient I Ricci squared minus gamma Ricci squared over r to the gamma plus 1 times gradient IR. You need this. You need the fact that gradient I of Ricci squared is the same as Rjk times gradient I Rjk times 2. And you need the fact you have to complete a square, so you need that the scalar curvature times the gradient of Rjk minus gradient IR Rjk squared is the same as r squared gradient of Ricci squared plus gradient r squared times Ricci squared. And the cross term is exactly something like this, minus 2r gradient Rjk gradient I Rjk. Okay? So this is the way you exploit up here the good term gradient Ricci squared. You can decompose it to collect this term, and the cross term here, you can take 1/2 of it and treat it in this way, replacing it by a derivative of f, and you can take the other half of it, estimating it against gradient Ricci squared, and complete the square. When you do all that, you end up with the fact that ddt of the thing we are interested in, Ricci 0 squared divided by r to the gamma, is less than Laplacian, the same thing. Let me just write f. Ddt of f is less than Laplacian of f. Here's f. Yeah, this is not. This is for f, and this is f0. Yeah, let's call this guy here f tilde, and then we have a tilde here that f is what we want, the trace-free part on r to the gamma. You get ddtf is less than Laplace f plus 2 gamma minus 1 on r gradient IR gradient IF, and then you get this square, you get minus 2 times r to the gamma plus 2 over r to the gamma plus 2 times r gradient IR jk minus gradient IR rjk squared. Then you get a negative term which we can throw away. If we can throw all the negative terms coming from the gradient, we can throw them away. We have this luxury times get this. And then we get the absolute terms. And the absolute terms, they have the following form. You get 2 divided by r to the gamma plus 1 times delta times Ricci squared times Ricci 0 squared. This comes from the denominator, from the differentiating the r to the gamma in the denominator. And minus 2 times a polynomial of 4th degree, where this polynomial you can compute from the absolute terms in this evolution equation that I had before. Take these absolute terms here, which come up here, and combine it with this, then you get a 4th order polynomial which can be computed as the Ricci tensor squared, so it's Ricci to the 4 minus 1/4 times a tensor q, where q is the right hand side in the evolution equation of the Ricci tensor, so q is equal to minus 8 trace Ricci cubed minus 2 scalar curvature cubed and plus 10 r times Ricci squared. Okay, it looks frightening, but you can do the computation, you work it out. So p is equal to actually lambda squared times lambda minus mu times lambda minus mu, and you get plus mu squared times mu minus lambda times mu minus nu times plus nu minus lambda in Hamilton's notation times nu minus mu times mu squared, where lambda, where mu is lambda 2 and mu is lambda 3 in my notation. Okay? And now you show that there's a lemma. You show that this polynomial actually, when you actually diagonalize it and do some algebra, you see that this thing is something that is always non-negative. The p is always non-negative, and it is 0 exactly if all three of them are the same, all three principal curves, all three eigenvalues are the same, or if one of them is 0 and the other two are the same. So in the case where all the eigenvalues are strictly positive, this thing is also strictly positive. So you can show an algebraic lemma, say purely algebraic, by staring at this fourth order polynomial, that if lambda 1 if all the lambda i's are bigger than epsilon times the trace, for some positive epsilon, then it must be true that this polynomial is bigger than some epsilon, the same epsilon squared, times some, yeah, I think it's the same, it's just times 1 times the trace-free part of the Ricci tensor times r squared. So you get that the you get this thing strictly positive if you are not on the round sphere. And now look what we have here. We have delta times Ricci squared, Ricci 0 squared. And Ricci squared, notice that Ricci squared is of course bigger than 1/3 r squared. So here we have delta divided by 3 times r squared Ricci 0 squared, whereas this polynomial, because of our assumption, just algebraically is bigger than this epsilon times the same thing. So if we now choose epsilon less, epsilon is given, if we choose delta less than 3 epsilon, then we are done. Just choose delta less than 3 epsilon. And then we get that the right-hand side is less or equal to 0. This in a maximum. Right-hand side is less or equal to 0 in a new maximum. Right? Because in the new maximum of this function f, Laplacian of f is less or equal to 0, the gradient of f is equal to 0, this is a negative term, it's less than 0, this is a negative term because gamma is less than 2. So this is a negative term, and we have arranged the absolute term to be also negative. And therefore, f is divided by the initial data, and that proves the theorem. Okay, that's the proof in the three-dimensional case. Now, it is an absolute miracle and absolutely beautiful that you get away with the maximum principle. Right? You actually have a good term left over, and the maximum principle gives you the pinching condition. We have seen that for the general pinching theorem, more things have to be done, but notice that during the whole proof we've never used the Sobolev inequality, we have never used the diffusion term, the Laplacian, in any delicate way. We have just used the structure of the Riemann curvature tensor in dimension 3, that there is no Weil tensor, that we had a second contracted Bianchi identity that was important in the gradient estimate of the general pinching theorem. And we have used the algebraic structure of the Ricci tensor and the algebraic structure of the terms on the right-hand side of the evolution equation of the curvature. So we were just using the algebraic properties of the reaction terms in the evolution equation for the curvature to get first that Ricci curvature is preserved, and then we use the algebraic structure of these terms again to show that we can make this a polynomial strictly positive, so the negative terms win, and we get our pinching estimate with a definite rate. It only depends on the positivity of the Ricci curvature. Okay, let me finish this lecture on dimension 3 and on this tensor maximum principle with pointing out how the analogous computation and attempt to prove pinching would work for mean curvature flow. And if it works. So, analogy to mean curvature flow. Now, if you have ddt f equals mean curvature vector for a hypersurface in Rn plus 1, the standard metric, then you just have to believe me that you compute the ddt of the second fundamental form is equal to Laplacian of the second fundamental form plus a squared Hij. Now, from there, you see, you conclude immediately with our maximum principle that convexity is preserved. Right? Because if Hij times Vj equals 0, you see this is our Nij, then Nij Vj is just a squared Hij Vj is equal to 0. So there is no, it's just staring at it, convexity is preserved. Right? If we ever hit a zero eigenvalue, it will turn up. In fact, this is a very simple algebraic structure. It is in the space of eigenvalues. If you think of the lambda i's and lambda j's, then this vector field here as a reaction term is just pushing out radially. So since it's pushing out radially, this convex cone of positive matrices will clearly be preserved. In fact, this ODE, if you just look at the ODE part, will preserve any cone, in particular any convex cone. And with this general maximum principle that I made, that I showed to you in the last lecture, you see that therefore any condition that describes a positive cone in the space of eigenvalues of the second fundamental form is preserved. So technically any condition described by a positive cone in lambda I space is preserved. So, for example, positive mean curvature, convexity, positive scalar curvature, positive 27th elementary symmetric polynomial, and so on. So you have many conditions that are immediately preserved by this tensor maximum principle that I showed you in the case of Ricci flow. Now, the third remark I want to make is, if you compute now the same thing, you compute ddt of the trace-free part of the second fundamental form divided by h to the 2 minus delta. So you try the same thing that Richard Hamilton did in the case of Ricci flow. You can also do the same computation. You get the Laplacian of this thing. You get 2 times gamma divided by h times gradient I of this quantity times gradient IH. You get a negative term which looks like h to the gamma plus 2 times h times gradient IHJK minus gradient IHHJK. So you get sort of the same algebraic structure for the gradient terms because you have the Laplacian. So at the gradient and second derivative level, you get exactly the same thing as in Ricci flow. But at the reaction term level, you get something very different because this is just pushing out in direction of the cone. This is somehow respecting scaling in varying quantity. So if the delta is equal to 0, the evolution terms from the top and the bottom cancel out exactly. So and then you pay for breaking the scaling invariance here. So it turns out you end up with delta A squared times the quantity you're looking at. So you get the bad term that Richard Hamilton also got. Remember, there was a delta term in the evolution equation of this quotient. But in the case of Richard Hamilton, we had this polynomial p of fourth order, which was strictly positive and had a minus sign. So we were able to absorb this bad term with just apply the maximum principle. This strategy completely fails from in curvature flow. This term here, there's nothing to compensate. You have this bad term. So the Ricci flow strategy in this case fails completely. So in this case, it will be necessary to use the good terms that we have thrown away in the Ricci flow case and use the diffusion term in order to be able to deal with this term. So here, have to use the diffusion terms. Okay? But that's a matter for a different course. And it turns out in Ricci flow, you have to use the diffusion term when you want to get rid of the curvature conditions. But in the positive curvature case, in the pinching case, all you need is the maximum principle. And that's a good point to stop. Thank you.